minutes until 9:40.
上车好，后面同学把保电往前传。
所以我觉得里面传承是，等一下，应该不同他们不同，同样对。哦，这个是他一个，他那个只有限量全球这个130，是这边。
Okay, so I will continue with section 5.3 in the textbook, which is called the fundamental theorem of calculus. Last time I showed you already the first part. I will write down again the first part, which I showed you last time, but I will also at the same time state the second part. So the first part says if f is continuous, on the interval AB, then if I define a function capital F of x, which is defined as the integral from a to x, f of t dt, then this function is an antiderivative. Of small f. So this means if you differentiate capital F, what you get, the derivative is just small f. Okay, so in other words, if you take a function, you integrate it, and then you differentiate it, then you are back to the original function. Now the second part tells you the opposite. So if you first differentiate, then integrate, then you're also back to the original function. So this part I already proved last time. The second part, the same assumption, so f is continuous. On AB. Then the definite integral from a to b, f of t dt, will be equal to g of b minus g of a, where g is any antiderivative. Of small a. Any antiderivative is okay. Not necessarily this one. This is So let's assume G is an antiderivative. On AB. It's actually the open interval AB. Or I can use also on the closed interval AB. Then we know that from the first part we know that capital F is another antiderivative, also of small f. So we have two antiderivatives, G and capital F, okay, on AB. But we learned before if you have if two functions have the same derivative, then they are just related by a constant. If the functions are defined on an interval. So what we get is that there exists a constant such that g of x is equal to f of x plus c. Where this f of x, this capital F of x is the f of x from the first part, defined like this. And then we only have to, okay, so the integral from a to b, f of t dt. This of course is by definition of capital F is just f of t minus f of a. That's just the definition of, using the definition of f. But capital F and G are related by this constant. So you see that you can replace capital F by G of B minus C. Minus, and you can replace F of A by G of A minus C. And the main point is now here, because this is G of B minus C minus G of A plus C. And you see the C cancels. So what you get is G of B minus G of A, as I claimed. So in fact, here you can choose any antiderivative, okay, G of F, and you can use it in order to evaluate the definite integral. So this means in order to compute the definite integral, we have now last time we saw the definition of the definite integral. If you want to compute it, one way is you just write down the definition. You get the limit of the Riemann sum, and you try to evaluate the limit. This is what we did last time for a couple of examples. Okay. Now this second part of the fundamental theorem of calculus gives you an entirely different way of computing the definite integral. Namely, if you can find an antiderivative of small f, any antiderivative, okay, then you are able to evaluate it. Actually, the first part tells you there is always an antiderivative, namely this one, but this one would be useless for evaluating the integral, right? Because it also involves the integral. Okay, so this one is useless. So you have to find one which is not expressed as an integral in order to compute the integral. Also, these two parts tell you that differentiation and integration are inverse operations. They behave like inverse functions, right? Because if you first integrate and then differentiate, you are back to the original function, and the other way around also. So it's like a little bit like composite function of a function with its inverse. The second part of the fundamental theorem of calculus, actually this comes a little bit as a surprise that integration becomes so easy. If you consider the examples from last time, they are now all very easy. You don't have to write down any limit of a Riemann sum and then try to figure out how to compute the limit. One example last time was the integral from 0 to 3 x to the cube minus 6x dx. Last time I used the definition in order compute it. Now it's much easier because it's easy to find here antiderivative. So this is my f of x. It's easy to find the g of x. X to the 4 over 4 minus 3x squared. This is clearly the derivative of this one is this one. So that's an antiderivative. So according to the second part, I only have to evaluate it at the upper limit and the lower limit. So it will be 81 divided by 4 minus 27. That's at the upper limit. At the lower limit, 0. Okay, so this is minus 27 divided by 4. So now this is becoming very easy. Actually, we usually write the integral if we have to. If this is our given integral, and we found the antiderivative, then what we usually write is g of x, and then a vertical line here, then at a and b. That's the way we usually write it. Another example, also from last time, was the integral from 1 to 3 e to the x dx. Also now very easy. Okay, because an antiderivative of e to the x is just e to the x, evaluated at 1 and 3. So this is e to the 3 minus, as we computed last time. And another example which, using the definition, we couldn't really solve because the resulting limit was too complicated, was the integral of the cosine of x dx. So here, the antiderivative of the cosine, also easy to find, is the sine of x, evaluated at 0 and pi half. So what we get is 1. In particular, this is very surprising because if you compare this with the limit, with the definition, you remember last time, so I defined this, what I call delta x. Delta x is, I divide this integral into n pieces, and then xi, which is pi I divided by 2n. Okay, and I have to choose a center point, which I always choose the right end point. So by definition, this actually is the limit n tends to infinity, sum I from 1 to n, and then the cosine evaluated as I pi divided by 2n multiplied with pi over 2n. It would be much harder to evaluate this limit, and then in order to get 1. Okay, that's just the definition of the definite integral. So it's rather surprising that there's such an easy way of computing the integral. Just guessing an antiderivative and evaluating it at the upper and lower limit. So actually we can also turn this, if you look at this example, we can also now turn this around. We can say if we have limits, if we have some limit, for instance, if we have given this limit to evaluate, we could just interpret the limit as an integral. And then compute the integral via this, the second part of the fundamentalism of calculus. The other way to compute it. And then you can also compute limits. Actually, this can also be used in order to compute limits. For instance, an example is if you have to compute the limit n tends to infinity of the sum I from 1 to n, then I divided by n to the cube, 1 over n. If you have to compute this limit, then you can just interpret it as an integral. This is the integral from 0 to 1 x to the cube dx. Because the delta x here is 1 over n. That's this here. And the xi is I over n. So you have to, if you pick this as sample points, then writing this by definition is just this. Okay, so you can turn it around. If you have to evaluate this limit, you can say, okay, I write it as this integral. And now for this integral, there is an easy way to compute the integral by the fundamental theorem of calculus. It's just x to the 4 over 4. It's 0 and 1, so it's 1 over 4. For instance, another example which also often occurs at exam papers is this one. For instance, compute this limit. Students often think this limit should be 0 because each of the terms goes to 0. Right? So this term goes to 0. This is the last term that goes also to 0. But that's not true. Because it's true that each term goes to 0, but as n is getting larger and larger, there are also more and more terms. In fact, this limit also easy to compute because you just have to, you again just have to write it. You have to recognize this is a Riemann sum. Right? Because if I write this with the sum notation, I have 1 over n, and then I have the sum I from 1 to n. And then 1 over 1 plus I divided by n. Now if I just do the same, okay, so this will be the integral from 0 to 1 dx over 1 plus x. I can also interpret this differently. I can say this is actually also the integral from 1 to 2 dx over x. Because now the delta x is still 1 over n. But now the xi is 1 plus I over n. So I can take the whole thing and say this is the function evaluated at the central point. So this is now. So if I interpret this like this expression in this way, I will get this integral. And now this the antiderivative is ln of x at 1 and 2. Okay. So you see it's ln of 2. So you see this limit indeed is not 0. It's ln of 2. Also one point which is important to emphasize is that the assumptions here are important. It's important that the function is continuous. This assumption here is important. Okay. You should be careful to check whether this assumption is satisfied. As an example, the integral from minus 1 to 3 dx over x squared. Here you have to be careful. You can it's not true that this is an antiderivative of the function of the integrand minus 1 over x, because if you differentiate it, it's 1 over x squared. It's an antiderivative. But this is not true. This relation doesn't hold because this function is not continuous on the interval from minus 1 to 3. In fact, it's not even defined. The function is not even defined at 0. Okay. So for an integral like this, you should not use the fundamental theorem of calculus. Okay. Because in fact, what you get here is the wrong thing. We haven't even defined this integral yet, because in order to define an integral, we need that the function is defined at the whole interval AB. Okay. So this symbol for us at the moment doesn't make sense. Okay. We will later on in section I think 7.8 in the textbook we will also give this here sense because in section 7.8 we will talk about what are called improper integrals. Okay, this actually is an improper integral, but our definition, which we saw last time, of the integral doesn't apply to this to a function which is not everywhere defined on the interval AB. Okay. That's the minimum requirement for our definition last time, that the function has to be defined on the interval a b in any point. Because by writing down the Riemann sum, we evaluate the function at sample points. And you might, if you choose for example point 0, then what is the meaning of the function evaluated at 0? Okay, so you have seen some examples. So you see, this is the second part is useful because it allows you easily to evaluate the integral. And the first part is also useful, as you saw last time. So the first part usually is used by because the first part tells you essentially that every continuous function has an antiderivative. Not necessarily an antiderivative which can be expressed in an easy way. Okay. There are some functions like if you have to compute the integral from 0 to 1 e to the x squared dx. Here the second part is not very useful because it's not easy to find an antiderivative of e to the x squared. If it's the function e to the x, it's easy, right? So the antiderivative of e to the x is just e to the x. But if it's e to the x squared, not easy to find an antiderivative. Okay. So you cannot just evaluate it by the second part is kind of useless. In fact, it can be proved. This is something we are not proving in this lecture. If you are not studying mathematics, you will never see the proof of this. It can be proved that the antiderivative of this function cannot be expressed in terms of the functions we know, okay, which are exponential functions, logarithmic functions, trigonometric functions, inverse trigonometric functions, and then essentially root functions and polynomials, rational functions. These are the functions we know, right, which we use. And if you just use those functions together with combining them via addition, subtraction, multiplication, and quotient and composite function, via this operation, it can be proved it's not possible to write down the antiderivative of this function in terms of the functions you know. Okay. So I told you last time, but of course this function has an antiderivative, e to the x squared, because it's a continuous function, right? So it must have an antiderivative. And actually we can write down one antiderivative, namely we can say the integral from 0 to x e to the t squared dt. That's an antiderivative, right? But the reason why we don't want this kind of antiderivative is because it contains an integral. Right, so it's kind of useless. It's obviously useless in order to evaluate this. Because if you say, okay, that's an antiderivative, now I use it to evaluate this, and this is f of 1, yeah, that's true. But that's just writing down the same thing twice. Right? So if you have a function and you can prove that the function cannot be expressed in terms of the antiderivative of the function cannot be expressed in terms of the function you know, okay, then one way which is usually done is you just give it a name. You define it via the integral. You give it a name. Okay, so you say this is a new function. This is an important function in probability theory. Okay, fundamental importance in probability theory. So actually, this function is necessary to know this function. So we just give it a new name. And if you use you don't have this function on the pocket calculator, but you have like sine and cosine and so on usually on the pocket calculator. But if you use a more advanced mathematical software like Maple, which I showed you before, then if you give Maple this integral, Maple can evaluate it, this integral, but in terms of this function. So the first part also is useful because it tells us every function has every continuous function has an antiderivative, and if we cannot write it down in an easy way, we just define it via the integral. Like this, there are a lot of functions in mathematics which have been which you haven't heard before yet, which you haven't heard about in high school, okay? But which are defined via integrals. Okay. Like last time I showed you the Fresnel function is one, the liquid functions of first and second kind. There are a lot of functions, hundreds of functions. told you also before, actually, one way of defining logarithmic functions is also via integrals. Because if you have to compute the integral from, let's say, write it in general form. If you have to compute the integral, this integral, okay, if n is not equal to -1, it's easy to have an antiderivative. This one is an antiderivative, right? Only the case n is equal to -1 is special. Okay. So I told you before, if we one way of introducing the logarithmic functions is to wait until one has the fundamental theorem of calculus. Okay. And then if you hadn't seen logarithmic functions before, here you would be in a very strange situation. Namely, if n is not equal to -1, it would be easy to give an antiderivative of this function. But if n is equal to -1, it wouldn't be possible if you hadn't learned about natural logarithm before. Okay. And then we just say, okay, but according to the first part, it's a continuous function. 1 over x is a continuous function on for instance, on the open interval from 0 to infinity. So there must be an antiderivative there. And then I just define it. So I just defined an ln of x. By definition, this is then the integral from 1 to x et over t. It's a new function, and you can study the properties of this function via this definition. For instance, you know that the derivative of this function is 1 over x. You know the second derivative of the function is minus 1 over x squared. So the second derivative is always negative, so the function must be concave downward. The first derivative is always positive, so it must be increasing, and so on. You can study properties. And then you slowly start to understand, okay, how this function behaves. And you can also prove like that the ln of x times y is equal to the ln of x plus the ln of y, and so on and so on. Okay. And you immediately get that this is a continuous function because of the first part of the fundamental theorem of calculus. It is even differentiable function. Okay. That's actually the best way of defining, or one of the better ways of defining logarithmic functions. And once you have defined logarithmic functions, you say, okay, because this function is obviously 1 to 1, so it must have an inverse. So the inverse you call e to the x. And then you have also defined e to the x in a clean way. That's a much better way of defining exponential functions than the way you saw in high school. Waiting until you have integration available, and then to introduce these functions. Okay, any questions to this? Of course, if you define a function like this, the question is how to evaluate it. You can always do it numerically, right? Because the integral is defined as a limit of a Riemann sum. You just take n large enough, you evaluate the Riemann sum. But that is not a very good way. Next semester we will learn a much better way of evaluating functions like this. Using what is called scalar series expansion. So because of this, of the second part of the fundamental theorem of calculus, it makes now sense it seems to be necessary to give an antiderivative to use a notation for the antiderivative of f. Okay. Otherwise, I always have to say g is an antiderivative of f. Okay. And the notation we are going to use is what is called the indefinite integral. So we don't write. This is motivated here by this result. So we don't write any upper and lower limit. So the indefinite integral. This is by definition is an antiderivative. So this is an antiderivative of f. That's the indefinite integral. I could have used this notation already in section 4.9 when I talked about antiderivatives. I could have used this. But when I talked about antiderivatives, that was before I talked about the definite integral. Okay? Then this symbol, there wouldn't be a clear motivation why using this symbol. This symbol comes from a sum, but the sum is related to the definite integral, the definition of the definite integral. Okay, but the reason why we use this symbol is because of this second, just to have a notation for antiderivatives. Then we can also write that the integral from a to b, f of t dt, is equal to the indefinite integral of f of t dt, and then evaluate it at a and b. That's the way we usually write it. And all the rules you saw before for antiderivatives, you can now write with this notation. So, for example, we had before a rule which said if you have an antiderivative of small f and an antiderivative of small g, then the antiderivative of f plus g is the antiderivative of small f plus the antiderivative of small g. Okay. And now you can. It's a little bit awkward to say it like this. So it's, but now you have the easy notation for it. So this just means that the antiderivative of f plus the antiderivative of g is the antiderivative of f plus g. So this is satisfied by. That's what I just mentioned. Or you have before we saw a rule that if you find the antiderivative of small f, then an antiderivative of c times small f is c times the antiderivative of small f. Okay, now easier to write for us. Okay. Antiderivative of c times f is just c times the antiderivative of f. That's what I mean. Okay, so now this symbol is more convenient not to write this kind of relation. Or the antiderivative of certain functions like cosine of x dx. That's sine of x. Just to clarify this, usually we write not this symbol is we write it's equal to not only one antiderivative, usually all the antiderivatives. If the domain is interval, so that's why we usually write here plus a constant. Okay, because on the right hand side, if you have a symbol like this on the right hand side, it's actually a set of all antiderivatives. That's why plus we usually write plus c. So for instance, the antiderivative of this function here it's minus 1 over x plus c. Okay. You could object here. You could say these are not all the antiderivatives because of all antiderivatives. Of 1 over x are given by the following functions: 1 over x squared. Minus 1 over x plus c if x is larger than 0. And if x is smaller than 0, you need another constant d. So you might have here 1 and here 2 if x is smaller than 0. These are all the antiderivative of this function. If the domain of this function are all real numbers without 0. If the domain of this function is a closed is an open interval, for instance, the interval from 1 to 2, okay, then the set of all antiderivatives is indeed this set here. So usually what we write here on the right hand side is the set of all antiderivatives, assuming that the domain is an open interval. Okay, that's why plus c, because we learned before if you have two functions on the open interval and the derivative is the same, then the functions just differ by constant. Okay, just to clarify, this is also clarified in the textbook. actually has, if you can also interpret this as in physical terms. If I write it in the following form, so the integral from a to b, then the derivative of f of x dx, so this is equal to f of b minus f of a. That's what the second part says. So if you differentiate first, then integrate you back to the original function. But if you interpret this in terms of physics, so this here is a rate of change then. Okay. And this here is what is called the net change. So in terms of physics, this the second part says that the integral over the rate of change is equal to the net change. In the textbook, this is called the net change theorem. It's just a reformulation of the second part of the fundamental theorem of calculus. So this is the integral over the rate of change of the quantity equals net change. In the textbook, you have a lot of a couple of examples, physical examples from physics. For instance, if m of x is mass, the mass of so what is the interpretation of x? So in the textbook, the example is the mass of a rod measured at distance x from the left endpoint so you have a rod like this made from some material. This is the left endpoint, and m of x is the mass of this part of the rod. Okay. Then actually in physics, usually you don't. The first thing you have is usually not the mass itself. The first thing you have is the rate of change of the mass, which is called the density in physics. So the derivative, that's called the density. You can think about the density like in every point of the rock, it tells you how much mass is concentrated there. Okay. And then this net change theorem just tells you that if you integrate the density, so you start from some point A until some point B, and you kind of, the integration is, you can think about it as adding up the density. The density tells you at every point how much mass is concentrated there. Okay. Then what you get is just the net change of the mass. So the mass from A to B, that's what you have here. So m of B minus m of A. So usually in physics you often have a rate of change. That's the first thing you have. If you describe masses, usually the first thing you have is the mass density. Okay. So for instance, you have a plate, and you know on the plate for every point how much mass is concentrated there. The concentration means you have the rate of change of the mass at this point. Okay. And then adding up them, summing up them, that's done by the integral. Okay. It will give you the total mass. That's also So that's also the net change theorem. So the integral over the rate of change is equal to the net change. Another example in physics is usually, I mentioned this before, if you describe a movement of an object, okay, before you know the position, what you usually know first is the velocity. Actually, it's even a step further. The first thing you usually know is the acceleration. Okay, because a movement usually is caused by a force. Okay, and the force will result in the acceleration. So usually the first thing you know the acceleration. Okay. And then the acceleration is the rate of change of the velocity. So if you want to go back to the velocity, you have to integrate over the acceleration, okay, by the net change theorem. And then once the velocity itself is the rate of change of the position, so you have to integrate once more. Okay. So in physics, actually, you very often you have the first thing you have is the rate of change, okay. And then you use it in order to find the original property. Okay. And the way to do it is using integration. So if S of t is the position of an object, that's time t. So the derivative of the position, that's what I just said, this is the velocity. And the derivative of the velocity, that's the acceleration. And if you want to know the position, if you integrate for instance the velocity, okay, so that's the velocity is the rate of change, so that's then the net change of the position. So this will be S of t2 minus S of t1. That's called the displacement. If you're interested, because the object might move here we consider the movement is on the line. It might move forward, also backward. Backward is the x becomes negative. That means we are moving backwards. Sorry, the velocity becomes negative, and you are moving backwards. Okay, but here, if you move first forwards and backwards, then what you get here is the position at the end minus the position at the beginning. Okay. If you want to know the total distance traveled, that will be different. Then you have to compute. You have to take the absolute value of v. So this will give you the total distance traveled. Which means that if you are traveling forward, counting positive. If you're traveling backward, then it's actually negative. So here it would be negative. Okay? Count is negative. But now, if I have an absolute value, also count it positive. Okay? So if you're starting from some point, you move 1 meter and then you move 1 meter back. Here you will get 0. The displacement is 0 because your end position is the same as the original position. But here it will give you 2 meters because you have traveled 2 meters. So sometimes you also have to compute integrals where you have an absolute value in the integrand. Okay. Now how to compute something like this, because it would be harder to find the antiderivative. You just need to break it into pieces. Okay. Because if v is positive, you can remove the absolute value. So you just break it into pieces where v is positive and v is negative. And then you can do the integral. Maybe an easy example. Let's do an easy example. It's the example from the textbook. This is a particle moves along a line. Along a line, straight line. So that its velocity satisfies v of t is equal to t squared minus 2t minus 8. I don't care about the units. The units are meter per second. Okay, but I don't care about it. So what is the displacement? So t from 1 to 6, and what is the distance traversed? For t is from 1 to 6. So what you have to do is you have to compute the integral from 1 to 6 of the velocity dt. That's for a. That's what you have to do. So that's not complicated because that's a polynomial. So you have t squared minus 2t minus 8 and dt. So by the fundamental sum of calculus, this is t to the cube over 3 minus t squared minus 8t at 1 and 6. And then you evaluate the upper limit and you subtract the lower limit. So what you get is this. So it's negative, so this means the position at which you are at time 6, okay, it was before your position at time 1. So you traveled maybe forwards, but also you traveled more backwards than forwards. And if you want to compute the distance traveled, then you need to compute this integral. Now, how to compute this integral? For this integral, because the absolute value seems to be unpleasant here, but you only have to understand where is this positive, where is it negative. But you can write this as t minus 4 times t plus 2, right? dt. So you can write it in this form because that's obviously the same. And now you see this quantity here. If t is between 1 and 4, it would be negative. If t is larger than 4, it would be positive. So what you have to do is you have to break the integral into two pieces from 1 to 4. From 1 to 4, this is negative. So the absolute value of a negative number is a minus. So it's minus t minus 4 t plus 2 dt. And then from 4 to 6, this is positive. So you can just drop the absolute value. It's t minus 4 t plus 2 dt. And then you do the computation. That's not the issue. And then at the end you get. Of course, now you will get something which is not negative, something positive, because that's a positive function. You integrate a positive function. That's the distance traveled. So our problem now for solving integrals is now reduced to the problem of finding antiderivatives. Okay. So far we haven't systematically studied how to find antiderivatives. Or in other words, we haven't studied yet how to compute the indefinite integral. Because the indefinite integral is finding antiderivatives. So far the reason why we were able to integrate functions is because we know a lot about differentiation. So we can guess an antiderivative for some function easily, like e to the x, we can easily guess, okay, antiderivative is e to the x. Or for t squared, we know, okay, antiderivative is t to the cube over 3. But how about more complicated functions? Like what is an antiderivative of, let's say, arctangent of x? Not so easy to guess maybe. So we need also some rules for finding antiderivatives. More than the rules we saw so far. I already brought down some rules like if you know the antiderivative of small f and the antiderivative of g of small g, then the antiderivative of small f plus g is the antiderivative of small f plus the antiderivative of small g. That's one rule. But we need more rules like this in order to be able to find the antiderivative of more complicated functions. Or now after this, the question becomes how to compute the indefinite integral, because that's finding antiderivatives. We will systematically study this in chapter 7, also in section 5.5, which is the next section I want to teach, which introduces the first more advanced method for computing antiderivatives, namely what is called the substitution rule. Substitution rule. So, for instance, if you have the indefinite integral, for instance, this one, this indefinite integral. So indefinite integral is just a way of writing, okay, I want to find the antiderivative. Yeah. Of course, I could try to guess, try to find the antiderivative just by guessing. If I'm able to guess it, then I know already the solution. But we want to have some more systematic ways of finding antiderivatives. Now, if you see this function, you maybe realize something. Namely, this here is a composite function. The outer function is the square root. The inner function is 1 plus x squared. This is just this part, right? It's a composite function. But you realize something. Namely, the derivative of the derivative of this is just 2x, the inner function. So actually, it would be easy here to guess the antiderivative because that's just something you obtain from the chain rule, right? But there is also another way which uses substitution. I show you first. So let's assume we substitute the inner function as u. So u is equal to 1 plus x squared. Now. I'm doing something which is not really correct. Okay? We will see this frankly will work. So if I know that u is equal to 1 plus x squared, then du over dx, that's the derivative of this one, is 2x, right? So I would like to write this, but that's not. I'm not really allowed to do this. I would like to put this on the other side. That's not a fraction. Okay, so I'm not allowed to do this. Let's ignore this for a moment. Okay, so why do I want to do this? Why do I want to write it in this form? Because you see here. You see here as well. Again, I'm not allowed to do this because this is one symbol. I'm not allowed to say this is something multiplied with this one. It doesn't make sense. It's just a way of writing an antiderivative. Okay, so actually I'm not allowed to break this into pieces to say, okay, I put this and this together. This doesn't make sense. Okay, but let's ignore this for the moment. This becomes then the u, and this becomes just the square root of u. Now it's easy. Now it's easy to find an antiderivative. That's much easier function than this one. Okay, now it's we know if it's u to the n, it's just u to the n plus 1 divided by n plus 1. Unless n is equal to minus 1, which is not the case here. So we have u to the 3 half divided by 3 half. That's constant. And now I just plug in for u, I plug in again 1 plus x squared, and then 3 half. Maybe I write it's a little bit strange. I write a fraction here. I write it 2 over 3. And then 1 plus x squared with 3 half plus a constant. On the way of finding this, actually this step was wrong. This is the step I'm not allowed to do. Also this step I'm not allowed to do. It's not a correct way of doing things. But let's check whether this is the right answer. Because I can say now, okay, this is f of x. This should be the antiderivative of this one, of the integrand. Okay. So and then indeed, if you differentiate f, okay, then now by the chain rule, you get this is 2x, and then 1 plus x squared to the 1 half. The constant is gone, and this is exactly the integrand. This is weird, right? Because I'm doing things which are wrong. Yeah, in the way. So almost every step is wrong. Okay. Like this step is wrong because I'm not allowed, and this is not a fraction. I'm not allowed to write this. And this step is also wrong because I'm not allowed to cluster them together. Almost every step is wrong, but the result is correct. Weird, right? Strange. It's like magic. It works, but why? Because this is just a way of memorizing what is called the substitution rule. Okay. So that's not a proof. It's just, but whenever we use the substitution rule, that's the way we are going to do it, because that's the way to memorize the substitution rule. Okay. Now the substitution rule is the following theorem. So let's call it the substitution rule. So assume that g of x is differentiable. And f of x is continuous on the range of g. And the range of g, which is an interval. Then I claim that the integral derivative of g of x, f of g of x, dx, this integral will be equal to the integral of f of u, du, where the very variable u is now equal to g of x. So that's exactly what I claimed here. From here to here, this step to this step. Because from here to here, all the steps I explained here wrong. Okay. But you can memorize it because of this theorem. But of course, we have to prove this theorem in order to make this a valid rule, a valid way of computing the integral. Now how to prove this? The proof actually here is easy. I just compute this integral. I compute this integral and I compare, okay, and I see they are the same. That's the proof. Okay, so because I assume, so why these assumptions? This differentiable I need because otherwise I cannot write here a derivative. Okay, so differentiable is because in order to be able to write this derivative, why do I need that f of x is continuous on the range of g, which is an interval? Because then I know that f has an antiderivative. A continuous function has an antiderivative by the first part of the fundamental theorem of calculus. Okay. So because of the from the fundamental theorem of calculus, I should have explained. I'm going to denote it by FTC. From the fundamental theorem of calculus, I know that f of x has an antiderivative. Let's say capital F of x. Okay. Now, using the antiderivative, I can easily compute this integral because I know this is the result of the chain rule. Applying the chain rule to the capital F of g of x. Right. That's so. From this, I know that this integral, the definite integral of the derivative of g of x, f of g of x. Dx. So, because of the chain rule, I know this is capital F of g of x plus a constant. Because the derivative of this one is just this one. That's the inverse of the chain rule. So this is for this integral. Now for this integral, here I just said that capital F is an antiderivative of small f. So this is just the antiderivative of small f, which is capital F, so f of u plus c. And I said u is equal to g of x. So this is f of g of x plus c. So indeed they are the same. You see, the result is the same. So those integrals are the same. That's what I claim here in this theorem. I computed this one, and indeed it gives me the same solution as this one. Okay, so this proves this result here. But the way to apply it is the way you saw for this example I showed you before. Okay, so we make a substitution like this, and then we say d of u is equal to derivative of g of x, d of x, even so this doesn't make really sense. And then we say this d of x and this derivative g of x, you can replace it by d of u. That's this here. And g of x will be replaced by u. That's the way to memorize it. If you have seen that, I don't know whether you see the substitution rule in high school. If you have seen the substitution rule in high school, it's usually taught like with an example which you saw. But that's very, very strange because you know that all the steps are not really, you're not allowed to do it, so why should this work? So it's a very strange way of introducing the substitution rule. It eventually works because of this result which I proved here. And this result actually, it's just, as you see from the proof, this rule results from the chain rule. Okay. It's just reversing the chain rule. All the rules for the indefinite integral will be just reversing the corresponding rules for differentiation. Okay, so we make a break of 10 minutes until 10:55. Then we continue. same function, it's just constant. Because the main point here is I can choose any antiderivative for A. I don't need to use this specific one. This one will be useless in order to evaluate this integral because this outcome itself contains an integral. Up to a constant. The difference is the same as this one because the constant cancels. so let's look at some examples. Who has learned this in high school? Substitution rules. Is this taught in high school or not? No? 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 Okay. Let's look at some examples just to see how this applies. The theorem itself is actually not that important. It's more important the way you do it, like I showed you for the first example. Because you might say, I seldomly made the integral seldomly of this form, because that seems to be very specific, right? Only constructing examples, only like examples from the textbook, they are like constructed such that they are in that form. So you might think this is not really useful. But actually a lot of examples are of this form. So let's look at let's go through some examples. For instance, the integral e to the 5x dx. This doesn't really have this form. Because the derivative of the inner function is missing. The inner function is 5x. The derivative is 5. It's not there as a multiplicative factor. But of course that doesn't matter because we can write here a 5 and here 1 over 5 outside. Okay, so here of course substitution works. We usually don't use this kind of rule. We use what I showed you before. So u is equal to 5x. That's the substitution here. Then du will be equal to 5 dx. So you can replace dx by du divided by 5. Okay, so this will be the integral e to the u and then du divided by 5. Now you can compute it because you can take out 1 over 5 and the integral of e to the u is just e to the u plus a constant. And then you just plug in. You replace u again by 5x. So that's the antiderivative of this one. Another example. For instance, tangent of x. If you want to integrate the tangent of x, this is you realize this is also almost of this form because the tangent by definition is the sine of x divided by cosine of x. So you need a composite function and the derivative of the inner derivative as a multiplicative factor. Here the composite function is 1 over cosine of x. 1 over cosine of x is a composite function consisting of 1 over u, and u is equal to cosine of x. The cosine of x is the inner function, and the derivative of the inner function of cosine of x is almost the sine of x minus the sine of x. So this actually is really of this form, almost. So that's why it should work to use here a substitution u is equal to the cosine of x. Right, so then du is equal to minus sine of x dx. That's good, right? Because then this here becomes minus du. So this is then the integral. The minus I can take in front of the integral, and then it's just du over u. We can solve it. That will be the ln of absolute value of u plus a constant. Now we just replace again u by cosine of x. So it's ln of absolute value of cosine of x plus a constant. Right? So the integral which you want to compute doesn't necessarily have to be exactly of this form. Almost of this form is also okay. Here it's not exactly of this form because the inner derivative, the function g here would be cosine of x. The function f is 1 over x. And the derivative, any questions? The minus. Thank you. And the derivative of the inner function is the g is cosine of x. The derivative of g is minus sine of x. Almost, it's almost of this form. Minus is missing. That's why I have this minus here, which is just forgot. Okay, so you see, this is even though this form seems to be rather specific, it's actually there are examples where we can apply this. Meaningful examples like the tangent of x. So an antiderivative of the tangent of x is minus ln absolute value of cosine of x. More examples. So for instance, the integral 2x plus 1 dx. So again, you can say u is equal to 2x plus 1. The inner derivative is not a multiplicative factor, but the inner derivative is just 2. So du is equal to 2 dx. So this becomes the integral square root of u, and then du divided by 2. So it's 1/2, and then u to the 3/2 divided by 3/2 plus a constant, and this becomes 1/3, and then you replace u again by 2x plus 1 3/2 plus a constant. That's not the only substitution in here for this example. So sometimes you can use different substitutions. You will always derive the same result. Here, another possible substitution is you substitute also the square root. Also the square root. So here this didn't contain the square root. Here also the square root. I can do also this substitution. Why? Because now you see dw is equal to, if you differentiate this one, you get 1/2, and then 2x plus 1 minus 1/2 times the inner derivative times dx. But you see, this is just the 2 cancels, and this is just w to the minus 1. So it's dx over w. Okay. So in terms of w, this integral would become the integral of now w, but dx has to be replaced by w. So you have this. It's kind of even easier. Now this is equal to w to the power of 3 divided by 3 plus a constant, and you replace it by you replace w by this function, so you get the same result. Okay. So sometimes it's not only one way allows you to, not only one substitution allows you to solve the integral. So sometimes there are different ways of doing the substitution. Sometimes if you have different ways of doing the substitution, the result you might get might look quite different. Let's show you an example for that. So for instance, the integral x squared sine of x to the cube cosine of x to the cube dx. Here, for instance, you can use as the substitution sine of x to the cube, because the derivative of this is cosine of, by the chain rule, is cosine x to the cube multiplied with 3x squared. So it's almost like what this I substituted, and it's almost the rest up to a constant dx. So then this is equal to, so 1/3, and then the integral of u du. Right? And then this is easy to solve. So u squared divided by 2, so divided by 6 plus a constant, and you replace u again by sine of x to the cube. So sine squared x to the cube divided by 6 plus 6. But of course, I could have also used the cosine of x to the cube. No, because then dw is what is minus the sine of x to the cube multiplied with 3x squared. So now I substitute this one, and the rest is the derivative, almost the derivative. Okay, so that's almost the same, but I have a minus, so I have minus 1 over 3. Then the integral over w with dw. So this is now minus 1 over 6 w squared plus a constant. And if I substitute it back, it's minus the sine cosine squared x to the cube divided by 6 plus constant. You see the answer looks quite different, right? This I obtained with this substitution. This I obtained with this substitution. They look quite different because here there's a sine, here's a cosine. How can this be? How can they look so different? Because the difference is in the constants. There are different constants here. Because you know sine squared plus cosine squared is equal to 1. Okay. So actually there are different constants here. But this is the same class of functions. Because you can replace the sine squared by 1 minus the cosine squared. So you get more or less this. So if you use different substitutions, your answer might look quite different. Okay, any questions to this? More examples. Square root of 1 plus x squared x to the power of 4 dx. This if you look at it, on the first glance, this doesn't look at all like this. Because if you substitute 1 plus x squared, the inner derivative will be 2x. That's not what you have here. So it doesn't really look at this. It doesn't look at doesn't look like it's of this form here. If substitution should be successful, then it must be more or less of this form. Otherwise, substitution won't be successful. Of course, you can always do substitution, but maybe the integral you end up with is even more complicated than the original one. You want to simplify it. That's what you want to do. That's why you do substitution, because you want to end up with an integral which is easier than the original one. This doesn't look. If you see it for the first time, it doesn't look like this. But you have to. No, it's the wrong example. To the power of 5. That's what I want. Also, it doesn't look like this because the inner derivative of 1 plus x squared is 2x, not x to the cube, x to the power of 5. But you can write it in this form. So 1 plus x squared. And then you have another x squared and times x dx. Now it's indeed of this form. Because if you substitute x squared or 1 plus x squared, okay, if I substitute x squared, this is the inner function, then the outer function is the square root of 1 plus x times x squared. And here this is the inner derivative. So indeed you can substitute here u is equal to, you can also substitute x squared, but you can also use 1 plus x squared. Then du is equal to 2x dx. Okay, so this x dx can be replaced by du half. So this will be the integral of square root of u. And then this x squared becomes u minus 1 squared. And then du, and I have 1 half. But that's now manageable because now I can just expand. I can just expand here. So this will be u squared, so it will be u to the 5 half minus 2u to the 3 half plus u to the 1 half, u to the 1 half, and then everything du. Now it's easy to integrate. So this will be 1 half, and then u to the 7 half divided by 7 half minus u to the 5 half divided by 5 half plus 1 half u to the 3 half divided by 3 half plus a constant. And u has to be replaced again by this one. And you can do some simplification. I'm not going to do this, it's just straightforward. Like this 2 you can erase with this one. This you can write as 2 over 5. And these 2 you can also erase with this one. And you replace again by 1 plus x squared. So sometimes it's a little bit harder to see how to do the substitution. So this using the substitution rule also needs a little bit of experience. But if you do enough examples, it becomes rather easy. Sometimes it's actually quite hard to recognize which kind of substitution will be successful. For instance, this example, x plus 1 to the minus 3 half, from x minus 1 to the minus 1 half dx. This seems to be rather tricky to find the right substitution. This was used for the master program entrance exam in one of the engineering programs of NCTU. They use this example. This is a rather tricky one, but it's just written in a way that it's hard to find the suitable substitution. Because you have to realize that something like this should work. But you need to know you need to be very familiar with differentiation to see this. Because the reason is because the derivative of this one, the derivative of this function is rather easy. It's x plus 1 squared divided by, and then using the quotient rule. So the derivative of this one minus x minus 1, the derivative of this one, which is 1, then you have the dx. So this is just 2 over x plus 1 squared dx. Now, how is this useful? Because now you can write this as x plus 1 to the 1 half over x minus 1 to the 1 half. And then if I write because here I have minus 3 half, so now I have to write here 1 over x plus 1 squared dx. Now you see indeed it's of this form. Because here the outer function is, the function f is the square root, the inner function is, or the outer function is minus the square, f of x is x to the minus 1 half, then g of x is this function. And it's almost the derivative which is here. Okay, so you see that if you do this substitution, then what you get is u to the minus 1 half. And this here, because of this one I wrote here, becomes 1 half u. So I have the 1 half u. Okay, so this is actually u to the 1 half divided by 1 half. Another 1 half plus a constant. So the answer becomes actually very easy. It's just the square root of x minus 1 divided by x plus 1 plus a constant. But it's a rather tricky example, just because it's written in an unusual way. You can. It's actually, this integral is almost exactly of this form. It's just hard to recognize that it's of this form. Of course, this example is artificially constructed in a way such that it's hard to recognize that one can use substitution rule, just in order to put it on an exam paper. The substitution rule is useful, but the integral must be of a rather specific form, that this integral becomes easy. Okay? So it will be more useful than combined with other rules. Okay. So this is the substitution rule for the indefinite integral. So how about the definite integral? So how about the definite integral? Since the definite integral can be computed via the indefinite integral, of course you could just say, let's maybe look at the example, then it's easier to understand what we are talking about. So let's say this is the example. You can just say, okay, by the fundamental theorem of calculus, this will be the antiderivative of 2x e to the x squared dx. So it's the indefinite integral of the integrand evaluated at 1 and 2. And now here I can use this substitution rule for the indefinite integral. Okay, so by using the substitution u is equal to x squared, you get that du is equal to 2x dx, which is exactly what the factor here is. And then, so this integral becomes the integral e to the u du. So e to the u du evaluated at 1 and 2. But this 1 and 2 is in x, so I have to go back to x before I evaluated 1 and 2. So here this is then e to the u, and u is x squared, so it's e to the x squared. I don't have to write plus c because in order to evaluate the indefinite integral, the definite integral, any antiderivative will do. Okay, so like this, and now 1 and 2. And then this will be e to the 4 minus e to the 1. Okay. That's one way to do it. You go via the indefinite integral. But another way to do it is also changing the limits. When you do the substitution, you also can change the limits, but you don't have to go here back to the x again. So there is a corresponding substitution rule for the definite integral, where also the limits, upper and lower limit, are changed. Because here you can also say, okay, from this step on, I do this substitution, but also change the limits. Then I have here, and this seems to be equal to e to the u, and the 1 becomes 1 and the 2 becomes 4. And now if you compute this, this is e to the u evaluated at 1 and 4, then you indeed also get the same result. Right? So the difference is here I change to the u, but only in the integral. I don't do this for the limits. Here I do it also for the limits. But for this I need a corresponding substitution rule for a definite integral. And the corresponding rule is just works like I did it here. So I will write down the corresponding theorem for the definite integral. the corresponding substitution rule, but for definite integral. The assumptions are a little bit stronger. So we need to assume that the derivative of g of x is continuous. On AB, and f of x is continuous on the range of g. Then the definite integral from a to b, f of x, derivative of g of x, f of g of x dx is equal to the integral from g to a to g to b f of u du. So formally what you do is you do the substitution u is equal to g of x. Okay, but you also replace, because this a and b are in x, so you replace a by g of a, b by g of u. That's the value in u. And then you replace g of x here by u, and you have again that the derivative of u is equal to the derivative of g of x dx. So you replace this here by du. And now you don't have to go back to x again, okay, because also the limits have been replaced. Again, the proof of this is very easy. You just evaluate this, and you evaluate this, and you see it's the same. Okay, using an antiderivative of f, which you call capital of f, easy to evaluate. And here, using the chain rule. So the reason why we also need, the assumptions are a little bit different. Here we only need that g of x is differentiable. Here we need that g of x is in addition, not only differentiable, also the derivative must be continuous. The reason is because this is defined via a limit. This is not defined via a limit. This is just the antiderivative. It's just a way of writing the antiderivative of this